Hello class, today we will be discussing angular motion and the classical rigid rotor. So the rigid rotor is going to be our third and final model for energy, the first being particle in a box, the second being the harmonic oscillator. So the harmonic oscillator is an example of linear vibrational motion, but additional energy is taken up in rotational motion as the molecule spins in space. So let's define this. The rigid rotor is a three-dimensional rigid object rotating about an axis. And rigid assumes that rotational motion is independent of vibration. So essentially we imagine that the whole molecule is not really vibrating while we're looking at rotational motion. We look at it as being independent. So let's begin with looking at a quick example of a molecule like hydrochloric acid HCl, where mass 2 chlorine is much larger than mass 1 hydrogen. There is an axis of rotation that is perpendicular to the plane of rotation. So if we look down here, we can see an image where we have mass 1, and this would be hydrogen, and mass 2, and this would be chlorine. So they're connected by a covalent bond, and we have an axis of rotation that would have ideally been drawn through the center of mass, but I made it kind of towards the center here. But this is our axis of rotation, and it is a certain radius away from mass 2 and a certain radius away from mass 1. And the whole molecule is rotating about a plane of rotation, and this plane of rotation is perpendicular to the axis of rotation. So since we have two masses, we can simplify this whole thing down as being as if it were a single mass using our reduced mass formula. So the two masses simplify to a reduced mass, mu, using the formula mu is equal to mass 1 times mass 2 divided by mass 1 plus mass 2. By doing that, we can consider then that the plane of rotation, drawn now here in the plane of the paper, is essentially the mass of the molecule, and that would be the reduced mass. And as the molecule rotates, we have to consider certain elements. So for example, we have the radius of the whole species, and that is given from the center out to the edge. And then we have an angle shown here in phi, and that is the angle of rotation. And then as the radius changes, or as a position changes along the radius, as we go from perhaps this location here to here, we have a change in angle associated with motion. So we're defining r as being radius and Greek symbol phi as being our rotational angle. Now, in a rotating system, no forces are considered to apply the rotation. So this is an ideal rotating system. So no forces oppose the rotation. There's no potential energy. We're considering all of this again to be equal to kinetic energy. And only the radial component of acceleration is non-zero. And so the only component of acceleration that we're going to be concerned with is centripetal acceleration. So that's how a point along the perimeter of the plane of rotation is accelerating as it rotates. So let's define a few things. First, let's define position. That will simply be x, and that will be position x. Velocity will be defined as dx over dt, which is the change in position x divided by our change in time. Acceleration is actually the second derivative of position with respect to time, and this is the change in velocity divided by change in time. In the rigid rotor model, we need to consider angular velocity and acceleration. Rotational angle phi is measured in radians, where 2 pi radians is equal to 360 degrees. And here we have our angle is given with the lowercase Greek symbol phi. Angular velocity is defined as a change in that angle phi divided by change in time. And this is given the Greek symbol omega, absolute value. So change in angle phi divided by change in time is equal to absolute value of omega, which is equal to d phi over dt. Now, velocity, which is a change in absolute position over time, v, is going to be equal to r times that value. So r times d phi over dt is equal to r times omega. And the reason for this is that radius and angle change determine distance. So consider how a certain body might be rotating in space. So say you have the Earth rotating. If you were at the Earth's crust, you would be moving at a faster velocity relative to the Earth's core, and that's simply given that you're at a further radius, r, away from the Earth's core. But the angular velocity is the same. The Earth is spinning at a uniform rate. So angular acceleration, the second derivative of angle phi with respect to time, which would be equal to our change in angular velocity, d of omega over dt, which is equal to alpha, acceleration. So change in angular velocity omega divided by time is our angular acceleration. All three of these terms are equal to one another. So now let's move on and talk about energy. The energy of this system is all kinetic. Remember, we're considering this to have no potential energy, and that's because there's no resistance to the rotation. So our kinetic energy is going to be equal to 1/2 mass times velocity. For us, this is going to be a reduced mass. So instead of 1/2 mv squared, we have 1/2 mu v squared, where again, v is equal to r times omega. Now, if we were to square velocity, we would have v squared is equal to r squared times omega squared. So let's substitute that term in for velocity squared, and we get kinetic energy is equal to 1/2 mu r squared omega squared. Now, this term, mu r squared, has its own definition, which is equal to I, and that is considered the moment of inertia. So we can simplify our equation for kinetic energy by substituting I for mu r squared. And if we do that, we get equation 7.24, which is kinetic energy is equal to 1/2 I omega squared. And so that's it for the classical rigid rotor. And so now let's move on and talk about quantum mechanical rotation in 2 dimensions. So first, when considering rotation and vibration as independent from one another, this treatment only works given the following assumptions. The first is that rotation depends only on the angular components of center of mass. And the second is that the vibration depends only on internal coordinates of the molecule, meaning that the vibration does not have anything to do with the fact that the whole molecule is rotating. It's just the internal, whether or not mass 1 and mass 2 are vibrating back and forth. So the limits of these assumptions are as follows. Bond length depends slightly on rotation, as atoms of a rotating molecule will experience centrifugal force, which would affect vibration. So vibration and rotation are not completely independent from one another. So now that we're talking about a quantum mechanical model in an xy plane, it is now time to discuss the Schrödinger equation in Cartesian coordinates. So we're going to be building up to a 2-dimensional model, but let's first start with reminding ourselves what a 1-dimensional looks like, and this will look very similar to the particle in a box, where we have the Hamiltonian operator acting on psi of x is equal to energy times psi of x, and psi of x being our wave function. And so the Hamiltonian distributes to being the kinetic energy portion and the potential energy portion. So we have negative h bar squared divided by 2 times our mass, and our mass is the reduced mass. If this were a particle in a box, this would be m, times the second derivative of psi of x with respect to x, plus v of x times psi of x is equal to energy times psi of x. Now the potential energy, v of x, is equal to 0. It's all kinetic. So our equation simplifies to negative h bar squared over 2 mu times the second derivative of psi of x with respect to x is equal to E, our energy eigenvalue, times psi of x, our eigenfunction. So when we build up to 2 dimensions, our equation changes, and we get negative h bar squared over 2 mu times the sum of the second derivative of psi of x and y with respect to x plus the second derivative of psi of x and y with respect to y. And this is equal to energy, our eigenvalue, times psi of x and y, our new eigenfunction. And we can make a substitution given this known expression here. When radius is fixed at position r naught, r sub 0, the second derivative with respect to x plus the second derivative with respect to y is going to be equal to 1 over radius squared times the second derivative with respect to phi, our angle. Now, if we make this substitution, what we're left with is negative h bar squared over 2 times mu times r squared times the second derivative of psi of x and y with respect to phi, our angle. And that is equal to E, our energy eigenvalue, times psi of x and y, our eigenfunction. Now, next we're going to make one of the strangest substitutions that we've made in the class, and that since the wave function is dependent on an angle, for some reason we have to change it. So instead of psi of x and y, this wave function will now be written as large phi of angle phi. We haven't seen this symbol since our work function, but this is now going to be our wave function in the rigid rotor model. So anytime you see large phi, that is the wave function. And I'll do my best to keep calling it wave function, even though it is not a psi anymore. So if we substitute big phi in for psi of x and y, we get to equation 7.40, which is negative h bar squared divided by 2 times mu times radius squared times the second derivative of our wave function of angle phi with respect to angle phi is equal to energy, our eigenvalue, times our wave function phi. Now, the Schrodinger equation in Cartesian coordinates looks like this. We have our Hamiltonian operator acting on wave function phi is equal to energy times our wave function phi. And again, that looks like this. Negative h bar squared over 2 times mu times radius squared times the second derivative of the wave function with respect to angle, of phi with respect to the angle, is equal to energy times wave function. Now, our energy eigenvalue. Our energy eigenvalue for a particle in a box, that depended only on principal quantum number n. And so our eigenvalue equation looked like this. In a very, very small space, we have Planck's constant h squared times principal quantum number n squared divided by 8 times the mass times box length a squared. The energy eigenvalue for rigid rotor, however, does not depend on the principal quantum number n. It depends on a different quantum number, and that is the angular momentum quantum number m sub L, which we haven't seen a lot of since Gen Chem or if you were in inorganic. So our rigid rotor depends on angles. The angular momentum quantum number is m sub L. We also have a dependence on pi and radius rather than box length. So our eigenvalue equation looks a little bit different now. It is E of m sub L is equal to Planck's constant h squared times angular momentum quantum number m sub L squared divided by 8 times reduced mass times pi squared times radius squared. Now, we can simplify this a little bit. So h bar squared is going to be equal to h squared over quantity 2 pi squared, which when you square the denominator is equal to h squared over 4 pi squared. And we have h squared over 4 pi squared in our eigenvalue equation if we rearrange it a little bit. So in the numerator we have h squared, which is here. 8 and pi squared can be separated into 4 times pi squared times 2, and that leaves us with an expression here that is equal to h bar squared. So if we make the substitution of h squared over 4 pi squared, we get a slightly more simple eigenvalue equation. Energy is equal to h bar squared times angular momentum quantum number m sub L squared divided by 2 times the reduced mass times radius squared. Now once again, we have an expression here that can be simplified since mu r squared is equal to our moment of inertia. So we can take I and substitute that in for mu r squared, and we get our final simplified eigenvalue equation for energy, which is E equals h bar squared times m sub L squared divided by 2 times the moment of inertia, I.